Hello, good afternoon everyone. Welcome to the Good Brain. So today I want to do a full walkthrough of how you can analyze 16S bacteria rRNA sequences using Mothur. It's going to be a full walkthrough of their MySec SOP, and today is just going to be a part one of the video, which is about the data preparation. How do you get the data from the machines? How do you set up your computer? And how do you turn all this FASTQ that you got from a MySec sequencing machine into useful information? Okay, so the scenario is actually something like that, where it's being laid out to understand the effect of normal variation of the gut microbiome on host health, and they actually have a few mice that actually just feed them to get fat and actually measure the stability of their microbiome between days 140 to 150, and they're going to analyze that based on OTU, amplicon, exact sequence variants, phylotype, phylogenetic methods, and so on and so forth. So we're going to go a little bit deeper into number 4 over here on the next video, but today is once you get the sequence from the machine, which is a bunch of FASTQ, how do you set up your computer, set up Mothur in the pipeline so that we will be able to analyze those sequences into context and annotation and so on. So what do you need before you start? First of all is, of course, download Mothur from the website. You can actually find the website right here, and I'll also put it in the link description down below, so it will direct you to this MySec SOP website. So what you need to do is to go to download here. So there'll be example data from Source Lab, the Silva-based bacteria reference alignment, and the Mothur format version of the RPT training set. And beside that, you also need to download Mothur from their website as well as vSearch. So if you're running on Ubuntu, the sudo apt-get actually would not work. Depends on the scenario, because Ubuntu actually casts a different version of Mothur. At this moment of time is 1.42, and the MySec SOP require 1.44. So just make sure you check properly on their version number and you're not being confused on that. So you can actually check their version number somewhere here. Yep, 1.47. But as long as you're going through and then download their latest version of Mothur, it should work properly. Just make sure that your version between the two actually match up. So in this case, I'm running 1.47. I'll also put a bunch of reference and version number in the video description down below so that you understand what kind of machine I'm running on and what version of every single software I'm running on later on. Okay, so vSearch is also something you need to take note of if you are installed directly to the source code or some other compilation. It's actually a software for chimera detection. So just make sure that if you are downloading, you can actually go to download Mothur over here and actually just go for 1.48 or in this case 1.47. So how do you find that? Just go to release, go to 1.47, just scroll down here, and you can actually download 1.47. Depends on your operating system that you're running on, Linux 7, Linux 8, Mac OS, or Windows or Ubuntu. So you can use any one of them. They should behave exactly the same. Okay, so you should also download, like I say, the FASTQ file and unzip everything in the same folder. So what do I mean by that is actually you need to, okay, so first of all, you should actually have 1, 2, 3, the MySec SOP data. You should have the Silva bacteria, you should have the training set, and you should have the Mothur zip file. So what you do is you go to you create a new folder. In this case, I'm calling it analysis folder. You open it up and you open the MySec SOP data. And instead of actually just dragging the folder in, what you want to do is actually see all this raw data and then drag everything into the folder. Okay, do the same for Mothur, do the same for Silva, do the same for the training set. And I'll explain what individually what they do later on. So inside you should see no folder at all. And for Windows user, you should be able to see something like a Mothur.exe and a Mothur without an extension in the Linux and Mac OS. So once you've done that, you got everything in the same folder. We can go back to here. So okay, so just before we start, just make sure you're very clear on what we will be getting in the end of the video today. We'll get a final FASTA file, which is actually the assembled FASTQ that is generated from the machine. The FASTA should also be attached to a count table on how many times this sequence that appear in each sample that you have. In this case, we're going to have 10 samples. We should have individual of them, and how does the taxonomic information of each of the count table actually looks like. Okay, so I'm using Mothur in all interactive mode because I feel like it's a better way for you to understand individual steps, what goes in it and what's come out of it. So if you're more familiar, of course, you can use the batch file and scripting, which I'm going to show you later on how to do. But for first time user, especially you're watching this video, it will be better to run Mothur in the interactive mode and try not to rename anything in the meantime until you have successfully run everything once. So for those that want to analyze your own data set, I would also recommend do not actually slot in your data set on the first trial. Try to run it so that everything works, so that you make sure you have the correct system, correct version of all the software, and it works properly before you swap in your own software, just in case it's causing any error from that end. Okay, so let's head to the terminal, and basically what we're gonna do today is just copy paste everything into the format. So I'm not gonna provide my own script. You can actually go to this website and do what I'm gonna do right now. Okay, so what I do is I'll put the Mothur SOP on the left side, and I'll go to my analysis folder, which contain all of the things just now, and actually click on Mothur to actually start my interactive mode. It's that easy. So if you're running on Ubuntu, so you can actually go to the terminal in this case and go and actually navigate to your folder to the cd command and just type whatever folder that you want, and then just type slot Mothur, and you should be able to launch Mothur like as such inside Ubuntu. Okay, so I'm not going to do that from here. Okay, so let's start our Mothur analysis. So first of all is to make sure that you are in the interactive mode, make sure you are in the correct versions, and make sure you are able to see all of this. And you can actually type help just to see all the information that you want, and you can actually simply type something so that it will also give you a bunch of what is that called, function to actually referencing from. So this is super useful, especially you are missing out an S or not an S. For example, make biome doesn't have an S, or make share is shard and or share. Sorry, there's a D behind share, and this is super useful for this kind of invalid command. Okay, so does it work for clear? No, it doesn't work for clear. Okay, let's just scroll up then. Okay, so first thing first is actually inspect our sample data set. So let's go back to our thing just now. So in our sample data set, you can actually see inside my SOP data, this contain all of our FASTQ that we needed for our from the sample that's directly from the machine. We also have something called, where's my mock data? There should be something like mock data over here. So a mock data is, you can think of it like a spike. So they're spiked in so that after the analysis, we'll be able to ensure that whether we're doing it correctly or not by looking at the mock data. So we already know what's inside the mock data, but we're also gonna put in their summary. Sorry, we're gonna put it through the same pipeline to ensure that we are able to get the correct information out of our mock data. So the important thing here is mostly just all the FASTQs. Okay, so the stability batch is something we'll actually be generating later on in life. So getting started, first thing first is make file. Okay, so I'm not gonna use any kind of input directory, because the input directory, when it is a dot, actually means it's the current folder. We're gonna look for all the FASTQ sequence, and we're gonna prefix something called stability, which in this case is the name of the study. So they're gonna name it stability. You can name it any kind you want. Just make sure if you run this thing, don't change it yet. Otherwise you have a lot of trouble changing out all the individual script down below. Okay, so once you are done, you can actually see the output name as stability.files. So what does that actually mean is, let's actually open it and actually have a look at our stability files here. So you can see that stability file actually just lists out all the file in their pairwise scenario to actually just list out all the sample. These are the sample name, these are the forwards, these are the reverse, and this is the forward, right? No, this is the forward and this is the reverse, so that is able to couple and make the further analysis later on. So nothing more, just an index file, but it makes it a lot easier when you have a lot of different samples, so you make it automatically for you. Okay, so the first thing we need to do is to make the context. So make context is actually very straightforward. You just have, because you are sequencing forward and reverse. So what they do is actually just align the two and then slice on the side and make sure that the quality of the final sequence is above a certain threshold in this case, I believe it's 25, and they will just keep whatever that is left. So just remember, also be very careful with the processor number. If you don't have that much processor, don't put it in. And how do you check a processor number? I like to go to Task Manager, go to CPU, and you can look at your logical processor over here. So for people running Intel 12 Gen, I'm not too sure about performance of E-core and P-core, performance and efficient. You have to try it on yourself. I'm running an AMD, so I'm using all the logical threads that I have. So once this is done, actually it will just generate the contigs one by one over all our sample. It's a pretty small sample size, which is about 2 megabyte per FASTQ. If you have a large sample, this is going to take way longer, and just beware on the wear and tear of your SSD as well. Just make sure that you don't accidentally kill SSD while running a training set and so on. Okay, so once you're done, you have all these individual output from the make contigs, and what we really want over here is actually trim contig.fasta. So that is the one that is going to be useful for us. And also here you can see all the sample name as well as the individual sequence that is in each of the sample, and the total is 52,000 and so on in all the different groups. Okay, so we can actually check the information on the count based on using the summary sequence command right here. Okay, so we can see that our minimum is start, and we are ending, so we're starting at 1 with about 500 for some of the sequences, but you can see that in 97.5 percentile, most of them actually end in 253, and very little of them actually, oh yeah, they're all about 252, so that's fine. So what we need to do now is that we do not want the 500s, the 500 base pair long contig over here, so we're going to throw them out. Otherwise the rest looks pretty normal. I think there's some a little bit too much homopolymer as well, so we're going to actually just throw some of them away, and we're going to do, yeah, we're going to just filter some of them away with a max length of 275 over here. So we can actually just specify the kind of parameter inside make contigs so that you don't have to do the filtering later on. But in this case, I'm going to use a screen sequence here to actually remove the unwanted sequence that we do not want. Okay, so they should give you a slightly smaller file, and you can actually just have a look at the file just now with not this one. This is actually just what is the current working file as detailed by the, what is that? It's detailed by the what is that called command. So what you actually need is called summary sequencing from here. So you can actually have a look at what just happened over there. I think we're missing a thing. No, yeah, it's perfectly fine. So after the screen sequence, you can see that we should no longer has a long sequence file there. Do we have it? Okay, let's just do it again, just in case that because there's something funny is happening right there, so I'm not too sure what did I press. For those that are wondering how do I copy and paste command, once you copy it here from the browser, just press right click inside the command line interface, and that should help you to paste the command in. Okay, so once we're done, we're gonna run a sequence summary from here from the output, and we should no longer see those long command right there. No, it's still there. Summary sequence current. Yeah, I think that's referring to a wrong file. Let's just try this here. Yep. Okay, so we can see that we no longer have the 500 what is that called 500 base pair long contigs, so those have been removed, and we also have a lot less ambiguous base pair inside our sequences that we have. So once we are happy that we have this kind of result, it's time to move on to have actually processing improve in sequences. So the next one is actually just, first of all, reduce the waste of things, because a lot of sequence actually appear a large number of time. So what we need to do is to filter out those duplicated sequences by running a unique seq command. So this should give you a count table and a unique FASTA. So all the individual FASTA are unique, so you don't waste space storing all the duplication, and the count table will record how many times it's being counted for each of the sample, right? So you can also, again, run a unique seq to understand what are the current situation, and it should be exactly the same as just now, just that we have run from 128,865. We should duplicate down to 152. No, that's actually more. Oh, no, here, sorry. So number of unique sequences 35553, and just now we should not have that. Yeah, so we actually narrow down the number of unique sequences in our final sample. I hope I'm running the correct command. Stability, trim, context, count table. Yeah, it should be correct. Okay, so we have actually reduced down our unique sample by running that. Okay, so the next one, once we have all the unique fast style, is actually to align our unique fast style sequence to a reference. In this case, the reference sequence we're using is called Silva-bacteria fast style. So it's actually an organization that actually collect all this reference alignment, so we can actually align them towards. However, the experiment design here, which I did not mention just now, only use a section of the what is that called, the bacteria 16N's rRNA. So the whole rRNA gene is about 1,001 base pair long, but they only use a certain region, which is called the V4 region, and that region is actually from 11895 to 25318, something like that. I'm not too sure why is it more than 1,000. Maybe I'm wrong about the bacteria. But yeah, the V4 is only a section of the 16S rRNA, so we do not need the rest of the sequence on our reference. So this is supposed to actually just trim the other extra sequence down, so we don't align to the wrong region, resulting in a false positive. Okay, so once we finish the trimming, we're going to rename the alignment fast style into something called a Silva V4 fast style, which is a fast style containing only the V4 version. So you can actually see if you actually run a summary sequences, we should have like start and end, Silva V4 fast style, and we have where is our thing here. So 11895 to 25. Yeah. So so we only have the number because the number is only 13,000, but we cannot see from where to where, but we know the sequence is from there. Yep. So that's correct. Yeah, 11426 over here. Yeah, there should be slight variation. The number should be fine because the MySet SOP is written. They might have a different version of the files, and there's updates in file, and there's sometimes random seed generation. So a slight number difference between your data and the website is fine. But if it's 100 different, if it's like 2,000 different, or like completely different, then you might need to take note and go back up and rerun the sequence again, just to make sure you don't miss any steps out and you're missing a thing. Okay, so if the Mothur say it cannot find a certain file, most likely because you have not run that step, or because you're on Windows and Linux and they use a different, what is that called, naming system, you might have to actually go into your folder to check if your the name of the file name is exactly as what they stated over there, especially those that are like me using Windows over here. Okay, so once we align all of them, we should get a unique align. So you can think of align file with the same concept as a FASTA file, right? It's just a file with all the base pair and all the sequence information in. I don't think I should open it with Notepad, they're very big, but you get the idea. They're kind of a FASTA file inside, which is being aligned to the reference, and these are how they're being aligned. Yep, so there's something like that, so you need to remove. Yeah, that's not very important for now. So you can again use a summary sequence to check your align file. So you can actually see that you can actually substitute the fast style with an align file, and it would actually still work here. Okay, so we can check our align file using tool processor. It's quite slow. Okay, yeah. So you can see that the start and beginning of our align file is somewhere around here. The number of bases is correct because we have limit our number of bases to 252 as the beginning filter step and the screen sequence step. And we can see the start and beginning are here and here, but still we have a lot of like, so the problem now is that the 2.5 percentile started from 1968, but the 95 percentile is actually only until 1150. So you can see the minimum and the maximum, we got some outliers that align to not just wrong location, but they're very, very spread out. So we also want to remove those outliers so that we don't know they are wrong or right, but we usually do not want to consider them as part of our analysis since we don't really understand them and we don't know where they come from. So they might be important, but in this case, it's recommend usually to just remove them. Okay, there could be it could be some sequencing error, it could be some environmental contamination, it could just be like a cosmic ray hitting a computer, result in some wrong sequence. So we're gonna use the same screen sequence just now, just that we are start and end is 1969, which is just right after the start sequence, and 11551, which is just right after the ending sequence. And yeah, so we have some problem here with removing 3500. So I do have the same problem just now. So what I did just now is actually just remove the end. So it won't remove as big number of sequence as we have. So you can see that if I don't do that, my sequence is about the same. I have 35,000, they have about 16,000. So I have about double the number of sequence as per the original table, but that should be fine. That should not result in a big change in the downstream analysis. Okay. So next one, we're gonna filter them off because okay, so this is more or less like a data cleaning step, because when you align and we do the filtering just now, it introduces a lot of gaps inside our sequence, right? Because when I align, they'll usually the reference is longer, and whatever that your sequence is shorter, they'll actually align to different thing and result in a number of wasted space in between. Is kind of like a sparse matrix. So a filter sequences kind of just filter out all the what is that called, the dash sequence up there. So you can actually have a look on the here on before and after sequence. So what we fit in is unique good align, unique good align. So this is quite big, so I'm gonna try to open, but for those that don't have a very powerful computer, this is a very bad idea. Yeah, it's not, I don't think it's gonna open. Yeah, so yeah, you can see that these are all the dot and dash that we don't want. So because they're gaps in alignment, so what the filter is trying to do is to remove all the dot and dashes so that we can actually significantly reduce our size. And you can see that after filtering, this is what we have. They're really short and they're really easy to read and very easy to do any downstream further processing and so on. Okay, so once we're done that, you can see that we do have some number of sequence. We do have a lot more sequence than original. So this might be fixed when you're running it in the future, but it's still persisting on my current analysis over there right here. Okay, so once we're done that, once we start trimming, we actually can run another, oops, how do I delete that? Yeah, I can't. So once we have finished trimming, we can run another kind of unique sequences, because before and after the mapping, there will definitely be some of them that are exactly the same, but they're being mapped differently and there's some sequencing error. So we are gonna reduce down that to the thing, and we're gonna have a unique and table again, and we're gonna run something called the pre-cluster. So a pre-cluster is a step before the clustering process to try to understand where the sequence are more similar to another. It's kind of similar to hierarchical clustering process, where you look for similarity and you group them together. So you can know that this group is similar, this group is similar, this group is similar, and so on and so forth. They'll try to align them in that way. So you can see that now every single sample have their own map, and we again will get a fasta and a count table after we run the pre-clustering. Okay, so once we've done that, we can now search for finally the chimera. So for those that doesn't never heard of this word before, chimera sequence is a kind of sequence that are not natively there, but rather a new contig that is joined from two different biological genes. So this gene and this gene, they got break off somewhere during the isolation process, and they actually got joined together right before the sequencing process or during the sequencing process, so that it result in a new gene that doesn't exist. So I'm not too sure how research program actually kind of function. I will suggest, I will speculate that they actually just search for this gene. Do they map to other gene inside your FASTA file? And if this gene map exactly to two other FASTA file, they will just remove it. They'll just try to remove it. They did say that this is a little bit aggressive because they actually remove 8% the gene sequence right over here. But yeah, I'm not going to question too much on how they do it, but the logic is if there's a chimera inside the sample, this algorithm is going to try to remove that. So remember, these two are actually duplicated sequences. Chimera research will automatically remove the chimera, but if you do not want that, you can actually put a remove chimera equals to false and then remove it with remove sequence later. So it's just a 1 or 2 step process that you can choose from. Okay, so once we've done that, we can actually look how many sequence do we have. I do have a lot more sequence than the original and a lot less unique sequence than the than original, and my start and end is completely wrong. So something is completely wrong in my sequence analysis. Let's just go back and try to estimate where did I go wrong, and I might have what's it called, double run some of the thing. So let's go for the beginning on screen sequence right here. Okay, so actually just gotta make Contig. So because I did not run this just now, I suspect this might be the problem. And just for sanity, I'm gonna actually run the make Contig and then the screen sequence again, just to make sure that this thing definitely did not exist. Let's see if it works. So I do have 16,000 sequence. Okay, so I do not have the long sequence, so I'm correct. Let's run the unique sequencing. Well, it could be the sequence where I try to not trim the end though. So never mind, let's see. So far I don't have to run this. This one I already run. Align it again. Let's just align it again and see if the alignment generate completely different thing. Okay, so that looks fine. Doesn't look completely wrong. Let's just trim it with 1969 and 11551. I'm missing a bracket. Okay, so I take 16 sequences. So if I do a summary, I should get exactly what they have, 1340 and 1969. So that's perfectly fine. Let's filter sequence and remove all the dot and dashes that we have. So this is perfectly fine. And then I'm going to run a unique sequences after the filtering. Perfectly fine. And we're going to run a pre-cluster, which is the one that actually takes the longest amount of time. Not really. Yep. So we have 23 sequences. Yep, something is definitely wrong. Yep, 24 sequences. So this is wrong. Yep. So I cannot actually remove everything over because yeah, they removed 16,000 of them. So this sequence is definitely causing some problem. So let's just actually try to modify a little bit. Okay, since I cannot run it on the amount, where are you? Okay. So I cannot run it in 11551. I'm gonna run it on 11000 and see how much they actually remove from there. So they're removing 6 of them, so I can actually further increase it. 11550. Then they're removing 222 of that. So I got 116,421. So this is close enough. I'm gonna run with it and see what happens. So I'm not sure what I did wrong in the first place, but if you do know, just feel free to leave a comment down below. Doing things is alone is simple, but doing it in front of the camera has a completely different case on it, where things just seems to everything just seems to not work when they're trying to do it in front of the camera. So let's just try a summary sec and check if our sequence are actually still there. Fasta equals to current. Oh no, summary sequence. Yep. So we still have 16,000 of them, so we are fine. So let's just do a pre-cluster now. Okay, so our pre-cluster have 6,000 sequence, so that's fine. Let's try the chimera and see if we're able to properly do a chimera this time. Yeah, just in case you're wondering why there's so much output, the Chimera vSearch is actually not a Mother native program that adapt the vSearch from some other previously written program, which is why the output and the programs is slightly different, and it's also why called Chimera vSearch. So they actually adapt it from some other people. Yep, so now we have 2,000 sequence, which is actually very close to what we have with the original MySec SOP. So that should be fine, means we didn't miss out anything in this round. And yeah, it could be that I'm trimming it differently. So yep, okay, let's go back to what we are talking about just now. So once we're done the pre-clustering and remove all the chimera, now we have so many sequences. Now we have 2,500 sequences. We need to know where they are from. So the classified sequence actually is a way to understand what are the genus and species. I think it only go out to genus. What the genus, family, phylum of all the individual sequences coming from. And here they're using the reference train set over there, which actually contain the more taxonomy information of all the alignment and sequences. So the silver for me, for understanding, the silver is actually for the sequence of it, for you to align the sequence to, while the train set here contains the taxonomy information. I'm happy to be corrected though. I can't find I can't find a lot of information here. Okay, so once we classify the information, you can actually go in and actually try to look at it on the output. So taxonomy, something like that. So you can actually see that these are all the different taxonomy information of that, but it's kind of hard to read like that. So you can see this is one of the contigs that we have, and these are the information of the taxonomy. However, the problem here is every time you try to do a metagenomic sequencing, there are usually some contamination, for example, from eukaryotes, from mitochondria, from archaea, or just some of them that are not actually mapped to anything. So in this case, we're going to do a remove lineage to actually remove our host genome or some other environmental contamination such as mitochondria and chloroplasts, which actually have very similar 16S sequence from the bacteria, from certain amount of bacterial populations. Okay, so once we're done that, we're gonna finally run our summary text, and we can have a look and how many sequence that we have and all the different all of the different information that we're running at the current moment of time. Yep. Yeah, we can't actually do the taxonomy current. Yeah, I have no idea. It doesn't work. Okay. So I think you have to check the output here on the text summary. Let's just have a look. Text summary here. So yeah, so these are the taxonomical summary for all the individual text level, rank ID, taxon, and all the individual sample. You should be able to open this in your Excel file or some other R tool so that it's easier to visualize them, but we're not going to go deep into that. We're going to go into that on our second video. Okay, so now it's basically done. So you have created everything that you want, but before we actually generate our FASTFile and taxonomy file, we just want to ensure that we are doing it correctly, like it doesn't cause a huge error like we did just now. So we're going to do something called assessing error rates. So how does it work is, remember the spiking that we talked about in the beginning, where we have a mock file or mock FASTQ inside our sample. So those are added in as part of the analysis so that we know if our analysis has gone wrong. Okay, so first thing first is to get group, and here we're gonna actually how do I say this? So it is to get a grouping so we can isolate which one is the mock information. So we only want the mock information to come off right here. So we have 64 unique sequences. We have a total of 4,000 unique sequences in our mock data. And then we can actually use our sequencing error to actually understand what are the error rate in this case. So if you do want to have further information on what do they look, you can actually here big fast style. So these are all the sequence from our mock FASTQ, and this is the count table from all the mock FASTQ. So you can see these are the these are the name of the thing, the abundance and all the different. I believe is group information one. It will really have abundance for the group 6 mock sequence mock. Yeah, let's just not care about it for now. But yeah, these are the fast style from it, and the sequencing error will allow you to align your mock to a fast style over here and actually check if you're doing it correctly or not. Okay, so let's just check our sequencing error, and it should result in the sequencing error of 6.5 to the 10 to the minus 5. So we have a very, very low error rate with barely any wrong thing at all. It means that our sequence is fine. So even though I do not use exact same parameters as the tutorial provided, our error rate is about the same. So we should be okay to proceed with whatever that you have. So do put the mock sequence and the HMP FASTA into your analysis as well if you're running your own sample. I think that should help you to troubleshoot if you have any kind of error, any kind of error when you're doing a downstream analysis. Okay, so the next one is actually we're gonna actually just generate our distance between our sequence. We're gonna generate our cluster between our different FASTQ. We're going to do a make share file so it's easier for us to share out the file later, and we're going to do the refraction single. So these are all more or less analysis related command line to generate all the taxonomy, all the lists, all the refractions and all that thing, and all the OTUs. So we're not going to go into that for now, but here what I really need to emphasize is, first of all, the remove group and the rename file. So what do we do before we actually start our own analysis on our own sample, we do want to remove the mock data over here from the original data set that we created together so that it will not interfere with our downstream analysis. And once we're done, we're going to actually rename all of the fast style, the count file, the taxonomy file as something called final. Okay, so if you go back to your analysis folder right here, you can see that now you have generated 3 things that you actually want. The FASTA file, in this case, that contains all the information from your sample. The taxonomy file, which contains all the taxonomical information from all the individual contexts that you have actually aligned and actually get understanding from. And the count table, which actually contains all the information on the number of times that appear and the groups that appear. So I believe this is sample 2 and sample 1 and so on and so forth, some sort of thing like that. Okay, so basically what we have done today is to take all the FASTQ file. We have download all the required information, all the required software and sample data into a computer. We unzip them into an analysis folder, and once you've done that, go to mother.exe, go to the interactive mode of our mother software, and then we just go through individual steps on how to get all this FASTQ, make the context out, trim off all the edges, trim off all the overhang, align them to a reference, classify them based on the training set that we have, and in the end check with the mock information of FASTQ that we put in and whether we have done our thing correctly or not, and just all the cleaning step that we need to do before we actually get to this 3 file. Okay, so these are the 3 files that will actually move on from this step onwards, and we're going to actually try to analyze them, which is based on OTU, ASV, phenotype, phylogenetics, and all the other diversity type of measurement that we do, as well as the comparison of between the 2 groups and so on and so forth. But for now, I'm going to stop the video right here. It's already 39 minutes long, and we'll see you in the next video on how to actually understand the analysis of our sample, particularly what is distance 6 cluster mix share and refraction is actually about. For now, I want to say thank you for watching, and we will see you in the next video. Bye.